Imagine a world frozen solid, encased in ice from pole to pole. No life roams these frozen plains. Only glaciers move across them. This is not some distant planet starved of sunlight. According to a radical theory, this was Earth, 650 million years ago. No one knows what triggered this calamitous freeze. But if it happened once, could it happen again? Imagine the most profound ice age you can think of. Temperatures plummet to below zero, even at the equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
A snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
We would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Incredible though it may seem, the Earth may have frozen over completely. Scientists are finding clues in unexpected places. The story begins with a mystery. In the arid Flinders Ranges in southern Australia, layers of ancient rock hold unusual stones. These stones are foreign to the area. They are known as drop stones. The drop stones are embedded in an ancient sedimentary sea floor that formed around 650 million years ago. Tim Raub, a geologist at the Californian Institute of Technology, hunts for these drop stones at the Flinders Range.
This is an example of a drop stone, a piece of ancient rock that was dropped into the ancient mud on the sea bottom.
These drop stones are visibly different from the sedimentary bedrock around them. Something powerful must have carried them here. But what? Dan Schrag, professor of Earth and Planetary Sciences at Harvard University, believes the answer is glaciers.
We actually have ice cubes here that we've made with pieces of sand and gravel in them. So these ice cubes are like the glaciers that are taking rocks from the land, and then when we put them in the water, they'll actually melt and the sand and gravel will fall to the bottom, just like the drop stones on the ocean floor.
These drop stones are evidence that at some point, this area was covered in a thick layer of ice. But it's difficult to explain how ice could have covered the sun-baked mountains of southern Australia. Unless the continent itself was in a very different place. The continents haven't always been where they are now. They move very slowly across the Earth due to the movement of tectonic plates. 650 million years ago, around the time the Flinders Dropstones landed here, the continents were positioned very differently. Since the dropstones formed under ice, perhaps Australia sat nearer to the poles where temperatures were lower. To locate the position of a continent in the distant past, scientists study the magnetic identity of rocks. Certain sedimentary rocks contain magnetic particles. When the rocks form, these iron particles line up with the Earth's magnetic field. Near the poles, they align at right angles to the sedimentary layers. And around the equator, they align parallel to the layers. Even if the rock moves, the distinctive configuration of these magnetic particles remains the same and provides a kind of geological fingerprint of the rock. Professor Joe Kirschvink at Caltech Pasadena is fascinated by magnetism.
Magnetism is magic. I've even named my eldest child after a magnet, so I enjoy magnetism.
Kirschvink and his team analyzed the 650 million year old rock surrounding the dropstones. The results were unexpected.
That part of Australia was within 5 degrees of the equator, and it just was the most weird place to expect a glacier.
But Kirschvink had to be sure that this ancient rock still held its original magnetic signature. If the rock heated up after it formed, its native magnetism would have changed. Back at Flinders Range, Kirschvink's team uncovered clearly striped sedimentary rock that provided proof.
Here, tens of thousands of layers of mud grew one at a time, upward and upward, in a glacial lake at the edge of a 635 million-year-old ice sheet.
When this rock formed, layers of sediment built up in distinctive horizontal lines. By comparing the direction of the layers of sediment with the direction of the lines of magnetism, Kirschvink could determine whether the rock's magnetic signature had changed.
We can explain the process of magnetism with a simple eraser. If the rocks formed on the equator and gained their magnetism very early, we would expect the magnetic direction to be parallel to the bedding very precisely like this. And then, since the rocks are soft, if they get squeezed or deformed geologically, you would expect them to rotate like this, and the magnetism would shift with the bedding. On the other hand, if the rock had been squeezed and deformed first, and then gained the line of magnetism like this, we would see them warped relative to the bedding today.
If the rock still had its original magnetic orientation, the lines of magnetism would follow the lines of sediment. But if its orientation had changed, the magnetism would cut through the sedimentary layers. Raub drills into the formation to retrieve solid cores of the rhythmic rocks. Back in the lab, the team analyzes samples of rock using a custom-built hypersensitive magnetometer. This magnetometer measures the orientation of the magnetic particles in the rock. It confirms that the particles were aligned with the rock layers. Kirschvink was astonished.
Quite frankly, when I saw the original study, I didn't believe it. And what in fact we see is that they're like this, and as the rock was warped, magnetism warped. That proves conclusively the magnetism formed before the rock was solidified.
This discovery seems to provide irrefutable evidence that the glacial rocks formed close to the equator. Paul Hoffman, professor of geology at Harvard University, was intrigued.
So if there were glaciers close to the equator, where the temperature was warmest, one has to assume that there was also ice in higher latitudes where the temperatures were colder.
650 million years ago, Australia sat near the equator. And yet evidence suggests that its arid rocks lay buried beneath ice. And if there was ice at the equator, there would have been ice all over the globe. These dropstones became the catalyst for a radical theory: Snowball Earth. This is a theory about the most extreme ice age imaginable. And if it happened before, it could happen again. Our world has been through many periods of extreme climate change. But some scientists have proposed that 650 million years ago, the Earth may have frozen over completely. This radical hypothesis raises one crucial question: how could it have happened? Kirschvink proposes that the giant freeze was triggered by the same mechanism that lies behind today's global warming, the greenhouse effect. Except 650 million years ago, it worked in reverse. Greenhouse gases in our atmosphere act like an insulating blanket, trapping the sun's energy to keep Earth's temperatures mild. When the snowball began, scientists suspect that levels of these vital gases fell dramatically.
The Earth's atmosphere might have been filled with methane and carbon dioxide, and the Earth became addicted to this high-level carbon dioxide and methane in order to keep its temperature. Then, if some unknown event crashed the carbon dioxide out of the atmosphere, Earth might have run away into a snowball Earth.
If enough carbon dioxide had been pulled out of the atmosphere, an anti-greenhouse effect would have plunged the Earth into a deep freeze. But this theory is only possible if there's a mechanism that could pull all the CO2 out of the air. In fact, carbon dioxide is removed all the time through a process called silicate weathering.
Weathering is a geological term for the decomposition of rocks under the influence of the weather. It's a process that converts solid rock into soil. Now, its importance for the climate is that weathering consumes carbon dioxide, which is a major greenhouse gas in the atmosphere.
Carbon dioxide reacts with water vapor in the atmosphere to form carbonic acid rain. This acidic rain weathers limestone on land and carries away the eroded sediment to the sea. Here it builds up, eventually forming limestone on the sea floor.
So the presence of the limestone is the evidence that weathering is occurring.
The more carbon dioxide gets locked away in limestone, the cooler the Earth becomes. But if this is happening all the time, something must have amplified the process for the whole world to have frozen over. Again, clues lie in the position of the continents. The movement of tectonic plates continually shifts the continents around the globe. Today, a lot of the continents are located in higher latitudes. If the Earth cools, the continents near the poles ice over. The ice prevents the rocks beneath from being weathered by carbonic acid rain. This means that the weathering cycle is kept in balance. With less carbon dioxide locked away in limestone rock and more in the atmosphere, the planet warms. Scientists have worked out that 650 million years ago, the continents were clustered around the equator, where it's warm and wet. Consequently, the global rate of weathering would have been higher.
During the snowball Earth, we suspect that there were many more continents at the equator, and this would actually lead to a situation that would make the planet vulnerable to a global glaciation.
As the Earth cooled, ice formed at the poles, but because there were no continents in the higher latitudes, ice accumulated on sea rather than on land. There was nothing to regulate the weathering. The cooling continued unchecked, and the world got colder and colder. This runaway scenario is certainly plausible. But although extreme weathering could be behind an ice age, it doesn't explain how the Earth could have iced over completely. Geologist Galen Halverson from Adelaide University studies triggers of the snowball.
One of the hardest parts about understanding the snowball is really how it began. We think that it must have began like a normal glaciation.
Normally, living things help to regulate the Earth's climate by maintaining the delicate balance of carbon dioxide. Plants consume carbon dioxide. Animals produce it. These consumers and producers help to regulate the climate, ensuring the Earth is neither too hot nor too cold. If there's more carbon dioxide in the atmosphere, it gets warmer. This causes plants to grow faster, which in turn draws out more CO2 from the air.
So that is a feedback against it getting too warm. And in reverse, if it starts getting too cold, then the biosphere responds by not drawing down as much CO2, and that allows CO2 to go back up. So there's a sort of buffer in the form of life on Earth that prevents temperatures from getting too cold or from getting too hot.
But rewind 650 million years and witness a very different story. Life on land was in its early stages of evolution. Most living things were in the oceans. This half-formed biosphere could not prevent the Earth from swinging to wild extremes of temperature. Colonies of single-celled organisms called cyanobacteria were the first to photosynthesize. They pulled carbon dioxide from the surrounding water to precipitate calcium carbonate, and they used this to make dome-like structures of rock. Geologist Jim Gehling is an expert on these early life forms.
Temperatures were dropping at this time, 650 million years ago, for the very good reason that carbon dioxide, the principal greenhouse gas, was being taken out of the atmosphere and locked away on the sea floor.
This trapped carbon dioxide can still be seen today in stromatolite reefs.
This is actually solid carbon dioxide, and I can release that carbon dioxide after all those hundreds of millions of years when I put this weak acid on the rock. And there you see it erupt as the white bubbles of carbon dioxide spring out of the rock, go back into the atmosphere to take up their role all over again as greenhouse gases.
The more carbon dioxide the cyanobacteria locked away, the cooler Earth became. Our planet was hurtling towards a deep freeze that would last for millions of years. $650 million years ago, the Earth's temperature plummeted. Huge sheets of ice spread across the planet. Eventually, they engulfed most of the land and sea. This was no regular ice age. Ice ages are nothing out of the ordinary. We experience them every 100,000 years or so. They are mainly caused by small changes in the Earth's orbit, which alter its position relative to the Sun. When our planet receives less of the Sun's energy over a number of years, ice forms high in the northern hemisphere and advances down. At the height of the last ice age 21,000 years ago, these icy sheets reached down as far as New York. But the tropics stayed warm. Only about 30% of our planet froze. But 650 million years ago, some scientists believe the ice kept coming, until eventually, most of the globe was covered. What could have caused this runaway cooling? The answer must lie in how our planet keeps or loses the sun's energy. The Earth's surface is made up of land, open ocean, and ice. These all reflect sunlight to a different degree. The amount of light a surface reflects is known as its albedo. Deep dark ocean has a low albedo, since it absorbs a lot of sunlight. White snow and ice have a very high albedo, since they reflect more of the sun's energy back into space. Tim Raub demonstrates how dark and light colors heat up under the sun.
The temperature of a white car sitting in the sun is only 120 degrees. The temperature of a black car sitting in the sun is 144 degrees. The black car absorbed light, the white car reflected it.
White reflects more sunlight, keeping whatever it's covering cooler. The more ice that covers the Earth, the more of the sun's energy reflects back into space, and the colder the planet becomes. This cooling leads to more ice forming, which further increases the surface albedo. This is known as ice albedo feedback. And something may have accelerated this cycle of cooling even more. New research suggests that when seawater freezes at very low temperatures, its composition changes, and it can become more reflective. At the University of Washington's Polar Science Center, Bonnie Light studies the relationship between ice and light. In the cold room, she freezes buckets of salt water at different temperatures. One of the buckets is exposed to snowball Earth temperatures of -10 degrees. The surface of this ice becomes much whiter.
Okay, so this bucket contains seawater that was frozen in a cold room at 5 degrees above 0 Fahrenheit. And we consider this a good laboratory analog for modern-day sea ice on planet Earth. And you can see that the surface of it is kind of gray colored, dull appearance. And this bucket also has salt water in it, although this salt water was frozen at about 10 degrees below 0 Fahrenheit. And we consider the ice in this bucket to be a good analog for sea ice on snowball Earth because it's very cold.
At snowball Earth temperatures, the composition of sea ice changes, turning its surface from gray to bright white.
And you can see that these crystals in this case have started to collect at the surface of this cold ice. And so I can kind of scratch away these crystals, and you can see that this is basically just a deposit on the surface of this cold ice.
At -10 degrees, salt molecules in the ice begin to form tiny crystals.
If you can isolate them under the microscope, they look like little gemstones. They're really quite beautiful.
These bright crystals have a dramatic effect on albedo. The white surface scatters more of the sun's energy and reflects it back to the atmosphere, causing temperatures to drop even further. In the 1960s, Soviet climate modeler Mikhail Budiko demonstrated how runaway ice albedo could cause a cooling Earth to freeze completely. Like many of his contemporaries, Budiko was worried about the effects of a nuclear winter. Nuclear explosions create clouds of smoke and dust, which block the sun's energy and lower the Earth's temperature. Budiko developed a mathematical model to work out the odds of a global ice age. He showed that if the Earth's climate cooled enough for ice to form in the lower latitudes, then the ice albedo would rise at a faster rate. And once the glaciers reached a certain latitude, the Earth would tip into a snowball-like state.
Somehow or the other, the ice line, the glaciers, reach some critical latitude, around 30 degrees. And once they hit that latitude, very, very rapidly, the Earth would have been entombed in ice.
Budiko's groundbreaking work showed how this snowballing effect could create a totally frozen planet within just a few decades.
Budiko's work was extremely important in demonstrating that it was possible that Earth might slip into a climate catastrophe which was covered completely with ice. It had not been recognized as a possibility before that.
If the Earth became entirely covered in ice, nearly all the heat it received from the sun would be reflected back into space. The planet would become locked in ice. So if runaway freezing trapped the Earth in ice, how did it ever escape? Some scientists suggest that 650 million years ago, our entire planet was locked in an extreme ice age. It was a unique event, the result of a set of improbable triggers. Or so they thought. Then, in 1997, evidence emerged that it could have happened more than once. It came from glacial deposits in South Africa that were over 2 billion years old. Paleomagnetic evidence suggests that these formed near to the equator. Geologist Paul Hoffman believes this could be proof that the Earth froze over completely at least twice in its history.
The best evidence for a snowball Earth 2.22 billion years ago is paleomagnetic evidence from South Africa. There are glacial tills there, boulder clays, that formed very close to the equator.
This discovery raised the possibility that the snowball wasn't a single event, but a recurring condition. Scientists raced to find the trigger for this earlier deep freeze. The cooling appeared to coincide with the Great Oxidation Event. Deep in the ocean, some of the oldest organisms on Earth evolved a mechanism called photosynthesis. The ability to convert carbon dioxide into oxygen using the sun's energy. As these photosynthesizing microbes thrived, they had a profound effect on the Earth's climate. 2 billion years ago, our sun was weaker. Our planet relied on greenhouse gases like carbon dioxide and methane to maintain its temperate climate. But photosynthesis uses up carbon dioxide. It also produces oxygen, which destroys methane. The result, a double whammy. Levels of both these vital greenhouse gases plummeted.
You have a precarious situation. You have a planet that's greenhouse needs methane, and you suddenly evolve a bug that destroys the methane.
Maybe the first bacteria that photosynthesized crashed the carbon dioxide and methane from the atmosphere and triggered the first snowball Earth.
As oxygen production soared, methane levels tumbled. With the loss of that greenhouse gas, the Earth spiraled into a deep freeze.
It's kind of a frightening conclusion that a single-celled mutant bug destroyed an entire planetary ecosystem. Destroyed it. Turned it into a snowball for maybe 35 to 100 million years.
Some scientists now think that our planet has been encased in ice on at least 3 separate occasions, and each time under different circumstances. But these snowball Earth scenarios present a huge problem. If our planet was trapped in ice, how did it ever escape? Something must have caused a global meltdown. Evidence of the thaw is right here. On top of the dropstones sit layers of a peculiar reddish-gray rock. These layers stretch for miles in the Flinders Range, Death Valley, and almost everywhere where the glacial rocks appear. These are carbonate rocks, which form in warm, shallow seas. But here, they appear right on top of the glacial deposits.
So here's a sample that actually shows the end of the snowball event. So that's an ice-rafted stone dropped out of an iceberg. And these are little grains that also fell out of an iceberg. And immediately on top of that, without any break in sedimentation, is cap carbonate that's precipitating directly out of the ocean and accumulating on the seafloor. And exactly the same relationship is seen all over the world.
Their presence is evidence of a sudden and drastic temperature increase. Only one thing could have triggered this: a huge injection of greenhouse gases such as carbon dioxide. In order to melt Snowball Earth, concentrations of carbon dioxide had to be around 350 times higher than they are today. But if the whole planet was encased in a thick layer of ice, where did the carbon dioxide come from? Caltech professor Joe Kirschvink had a revelation.
I woke up in the middle of the night and said, that's gotta be it. It just dawned on me that these subaerial volcanoes, like in the Aleutians and the Yellowstone, these volcanoes sit and they spew CO2 into the air.
Even beneath the ice, volcanoes would have continued to release immense volumes of carbon dioxide. With the rest of the planet still ice-locked, there would have been no mechanism to remove it from the atmosphere. Over millions of years, levels of this greenhouse gas would have built up, eventually producing enough warming to offset the ice albedo. The ice melted, sending global temperatures spiraling upwards. As this melted ice water evaporated, it swelled the atmosphere with moisture, creating torrential rainfall. Carbon dioxide in the atmosphere acidified the rain. Acidic downpours rapidly eroded limestone, washing sediment down into the oceans. Here, layers of carbonate sediment accumulated on the sea floor to become carbonate rock. Dan Schrag demonstrates what could have happened.
Instead of carbonic acid from carbon dioxide, we're going to use a little stronger acid to make it go a little faster. This is nitric acid, and when we add it to the limestone, it will dissolve away the limestone and ultimately create a very clear solution. So you can see it bubbling away. And when this is added to the ocean, it reacts and creates the cap carbonates that blanket the top of the glacial deposits.
But still, not everybody is convinced that the planet was ever entirely covered in ice. Some scientists argue that the chances of life surviving a full-on snowball are virtually nil. Above the ice, the freezing conditions were too hostile, while below it, life was cut off from sunlight. Yet there is evidence that photosynthesizing organisms did survive the freeze. Single-celled cyanobacteria existed right the way through. Cyanobacteria can survive extremes of temperatures many degrees above and below zero. But if the oceans froze over, a thick layer of ice would have sealed them away from the sunlight. With their energy source blocked, they would have died out.
If you'd been diving on a tropical reef before Snowball, this is what you would have seen. Slime world, mounds of slime on the sea floor. And if you touch them, you'd find out that they're actually rock. A surface covered with slimy material, which is actually cyanobacteria, the earliest, the most primitive form of life that's been around for 3 billion years up until this point and is still around today.
Critics argue that nothing could have survived the ferocious conditions of a total global freeze. They maintain Snowball Earth was nothing more than a severe ice age with extensive glaciers and a belt of open water around the equator. Philip Allen, a geologist at Imperial College London, believes that the evidence for a frozen planet is flawed.
I am not in agreement with the Snowball Earth hypothesis. The major hole in the theory, as far as I'm concerned, is that the sedimentary rocks deposited during the glacial periods do not support the idea of a long-term global freeze.
Philip Allen's counter-evidence includes the ripple-like patterns in rocks formed 650 million years ago.
When you look at those sedimentary rocks, it indicates open water. The wind was able to blow over the water surface and form ripples, wave ripples on the seabed. So they are really conclusive proof of an open water surface rather than an ice-covered one.
Waves in an open sea left imprints in the sediment of the sea floor. When the water disappeared and the sediment turned into rock, the ripples remained. Allen and others propose an alternative to the snowball Earth. It's known as the slush ball. In their version of events, the Earth never froze completely. Some patches of open land and sea remained. But proponents of the snowball theory don't suggest that the frozen planet was without any open water. Schrag believes that life could have survived in ice holes around sources of geothermal energy.
Even in a completely ice-covered planet, there's still plenty of places where there are hot springs, geothermal heat from volcanoes, probably thousands and thousands of such little holes. And in many of those little holes, you could sustain life throughout the snowball Earth period.
The reality is, we may never know if the world was ever completely frozen over.
Sometimes people think of the snowball Earth like a cartoon, an oversimplified planet, but the real world is much more complicated than that.
Whether slush ball or snowball, everyone agrees there was a profound global freeze. And when our world emerged 635 million years ago, something unexpected appeared. Life, far more complex than anything that had gone before. After the Big Freeze, life on Earth exploded. Our planet, 650 million years ago. Temperatures plummeted, turning our planet into a hostile place. Yet somehow, life survived. And as soon as the frozen Earth began to thaw, it blossomed. And there was an unprecedented explosion of life on Earth. Before the deep freeze, life was primitive. Single-celled organisms and algae were mostly confined to the oceans. Shortly after it ended, the first multicellular animals appeared. The big question is, did the global cooling trigger this great leap in evolution?
Well, the best evidence is the coincidence in timing. The fact that the first fossils of multicellular animals occur less than 3 million years after the last snowball termination.
Shuhai Xiao is a geologist at Virginia Tech. He unearthed some of the oldest multicellular animal fossils in the world in a mine in southern China.
The fossils are really small. They're about ½ millimeter in diameter, so you can barely see them with naked eyes.
Under a microscope, he discovers that the fossils are very primitive animal embryos. Some fossils show clusters of 2, 4, 8, and more cells.
It was really exciting when we found those. Those are some of the earliest animal fossils, and they have found in rocks that were deposited almost immediately after the snowball Earth ended.
Fossils of these animal embryos date back to just 3 million years after the global freeze ended. That might seem a long time in human terms, but geologically, it's the blink of an eye. Over the next 80 million years, animal life exploded. In the Flinders Ranges in southern Australia, geologists have found some of the oldest fossil evidence of complex multicellular life. These creatures bear little resemblance to life today, but they offer clues to the genesis of early life. 650 million years ago, this area was beneath a shallow sea. Bizarre, soft-bodied organisms similar to jellyfish or flatworms lived on the sea floor. Some of the organisms got trapped in fine silt of tidal flows where they fossilized. Jim Gehling has been investigating these early animals.
Probably our ancestors lie in these rocks. This thing here, Dickinsonia, can best be described as some kind of a pancake or mat-like worm creature. It doesn't have a proper head, it has what appears to be a gut, very fine segments.
But this doesn't explain how the severe planetary freeze could have triggered a leap in evolution. What we do know is that there is a striking coincidence between the rise of oxygen and the end of the snowball. Oxygen levels rise following these global ice ages because of a chemical reaction between ice and sunlight. 650 million years ago, there was no ozone to stop the sun's ultraviolet light hitting the Earth's icy surface. This UV light reacted with water vapor to form hydrogen peroxide. The hydrogen peroxide remained in the ice for millions of years. But when the ice melted, the hydrogen escaped, and the peroxide converted into water and oxygen. Oxygen reached the same level as we have today. At roughly the same time, the first complex animals appeared. More oxygen enabled life to become multicellular. A single cell can take up gases and oxygen from water. Oxygen fuses across the cell membrane into the cell. However, when several cells link together, it's harder for oxygen to diffuse from one cell to the next. The pressure of oxygen needs to be higher.
You need to have a high enough pressure of oxygen to have a circulatory system bring the oxygen all around the body. After the last snowball Earth, oxygen seems finally to have been high enough to support hundreds, thousands, millions of small early animals on the seafloor.
Oxygen turned out to be the linchpin of evolution. The ability to use oxygen enabled life to become dramatically more diverse.
Oxygen gives us 20 times more energy, or more than 20 times more energy, than any other thing that we can breathe or that life can breathe. You can have bigger animals, you can have more active organisms, you can have plants that grow and transport liquids from roots to the leaves, and you can have birds energetic enough to fly. Without oxygen, we would all be slime.
A frozen Earth may have given early life a push forward. But if the world were to freeze over again, we'd struggle to survive. We know it's happened several times before. The question is, could it happen again? One factor in our favor is the sun. Over the last 4.8 billion years, it has been getting more and more active as nuclear fusion generates more and more heat. The sun today is about 6% warmer than 650 million years ago. So in the short term, another deep freeze is unlikely.
The sun is warmer today. That probably helps us out. But until scientists really understand what causes snowball Earths, I don't think any of us know whether we're in danger or not of a recurrence.
But there is one possibility that could result in another global freeze: a shift in the position of the continents. We know their arrangement influences the climate. If the majority of the continents were clustered on or near the equator, the Earth would be more likely to turn into a snowball. Cooling temperatures would cause ice to form in the open ocean of the poles, while weathering would continue on the continents. With more and more carbon locked away, temperatures would plummet.
If all the continents were near the equator, then the Earth could get colder and colder and sea ice could form and get to lower and lower latitudes, closer and closer to the equator.
Today, our world seems safe. Most of the continents are near the poles. But plate movement never stops. At some point, millions of years in the future, the continents may group around the equator once again.
I think it's possible someday, if the continents were in a very different position, maybe hundreds of millions of years from now, that we could indeed have another snowball Earth.
It's unlikely that mankind will be around to witness another snowball Earth. But the Earth will still be here. And just like it has in the past, our planet will survive and enter a new phase in its extraordinary history.
This is nature at her worst. Shredding buildings, drowning cities, killing thousands.
The hurricane is the most deadly and powerful system or phenomenon you're going to find on this planet.
They're the largest storms on Earth. How they gain such power is a puzzle with missing pieces. Scientists follow the life cycle of these killer storms, from birth to death, to solve the mystery. They are one step closer to parting the clouds, to reveal the anatomy of a hurricane. Hurricanes, nature's fury. A single strike can cost billions. Every year, hurricanes claim lives around the world, and they're becoming more powerful.
You have this whole devil's brew of things going on in a hurricane. Incredibly high wind, waves crashing on shore, intense thunderstorms. It's just an incredibly scary blend of things happening all at once.
Scientists struggle to predict where a hurricane will strike and how powerful it will become. Only by studying it from cradle to grave can scientists learn how it functions and perhaps forecast where and when it will hit. This is the story of science against nature at its most furious. Lives depend on the outcome. Over 80 hurricanes form each year around the world. Of those that form in the Atlantic, roughly 1/3 will strike America. The names are familiar: Andrew, Wilma, and Katrina. The future will bring new tragedies. And the race is on to understand how hurricanes work. Chris Lancy from the National Hurricane Center is trying to crack the hurricane code.
One of the primary goals of the Hurricane Research Division right now is to better understand the life cycle of hurricanes at their infancy, at their beginnings, at genesis, and to maturity, and then to the decay.
Ignition. The search for answers starts thousands of miles above the Earth. Satellites allow researchers to spy on a weather system born far out of sight of land. Images taken 22,000 miles above Earth reveal the genesis of the storm. 85% of major Atlantic hurricanes actually start in one of the hottest, driest places on Earth: Africa. In summer, the vast Sahara heats the air above it. As the air warms, it rises, climbing over 2 miles. The warm air pushes the existing weather patterns higher, forming an atmospheric disturbance. Scientists call this the African Easterly Wave. It travels west across Africa at about 500 miles a day. Converging winds on the east side of the wave trigger the development of thunderstorms, the seeds of our hurricane. Over the warm waters of the Atlantic, the thunder cells grow and merge. Atmospheric pressure within the weather system drops. Winds rush in to fill the gap and grow in strength. When they reach 23 miles per hour, meteorologists call it a tropical depression. Computers at the National Hurricane Center track every growing storm. Getting information as early as possible is crucial.
If we can't forecast, the genesis or beginning, we're going to be behind the curve in forecasting the rest of the formation of the storm itself.
Satellite data is vital, but it's not enough. They need to see inside the storm. That's the job of Jim McFadden, hurricane hunter.
You have to know what's going on in the storm full time. And the only way to get the information like the highest wind speeds, the lowest pressure in the center of the storm, is to actually put a plane into it.
The Hurricane Hunter's workhorse is the Lockheed WP-3D Orion turboprop aircraft, packed with scientific instruments and radars. They load data-collecting probes and fly out to meet fledgling hurricanes 5,000 feet above the waters of the Atlantic Ocean. The thunderstorms within the depression group together. Atmospheric pressure keeps dropping, causing wind speeds to increase. When they hit 39 miles per hour, the depression gets reclassified. It's now a tropical storm. The storm pulls in air over such vast distances, the airstreams actually curve. Greg Holland explains how the thunderclouds begin to spin.
It steals some of the rotation from the Earth system to actually give it that turning. It's an effect we call a Coriolis force.
The direction of the storm's spin depends on whether it forms in the top half of the Earth or the bottom. In the northern hemisphere, the Coriolis effect pulls winds to the right and makes the storm spin counterclockwise. In the southern hemisphere, the wind is pulled to the left, which makes the storm rotate clockwise.
If there was no Coriolis, the hurricanes probably wouldn't spin up because the low pressures would be filled and that would be the end of the storm.
Rotation alone can't turn a tropical storm into a hurricane. Up to 28 tropical storms form each year in the Atlantic. On average, only 6 become hurricanes.
You have to have a few kind of key ingredients. You can almost say it's like a hurricane recipe for things to begin. One of which is you need a bit of spin to get things going. Another key ingredient is you need thunderstorm activity. Hurricanes are fueled by the thunderstorms. And the third key ingredient is you need a warm ocean. You need waters at least 80 degrees Fahrenheit for enough energy to be available for those thunderstorms.
The warm waters of the Atlantic Ocean act as fuel for the growing storm.
It's sort of like you go down to the tank and fill up your car. You put a certain amount of energy, if you like, into the car, and then you can drive at a certain distance.
As the surface water temperature of the tropical Atlantic rises, trillions of energy-bearing water vapor molecules evaporate into the atmosphere. They rise higher, they cool, and condense into clouds. This process releases heat, which warms the air around it, pushing the clouds even higher. Now the storm towers 10 miles high. The air within is no longer warmer than the surrounding atmosphere, so it stops rising. The system flattens out to form an anvil cloud. There's still one thing that could stop the storm from becoming a hurricane. High-speed, high-altitude winds. These can shear off the top of the storm, destroying its structure and the flow of energy within it.
You need what's called a minimum of wind shear. And wind shear is just the changing winds with height, the difference between just above the ocean and about 8 miles up. If that wind difference is about 20 miles per hour or greater, hurricanes don't form.
In the growing tropical storm, the wind shear is low and it continues to gain strength. As the winds hit 74 miles per hour, it gets a new name. This is now a hurricane. It has the potential to become the most destructive weather system on the planet. The hurricane is 200 miles across and heading straight for land.
Whether you're flying into it by aircraft or watching from space from our satellites, then it's approaching its most beautiful stage. So people like seeing them to some degree, but we also realize the horrible problems that hurricanes can cause.
McFadden's Hurricane Hunter team have to fly into these killer storms. With data from the eye of a hurricane, scientists can estimate how powerful the storm might become. The center of the storm is still hundreds of miles away when the hurricane hunters hit the first rain bands. These are fierce clusters of thunderstorms that spiral out from the center. They form as water vapor evaporating from the ocean rises into rain-bearing clouds.
We usually pick our way through the rain band so that we avoid most of the severe turbulence in a rain band, and then on towards the eye wall.
The eye wall is a dense wall of cloud around the hurricane's eye. It's where the weather is most extreme. Here, winds can reach 200 miles per hour. The rain is torrential.
It's where a lot of the upward transport of moisture, the conversion into clouds, and the heating occurs to get the cyclone going. So this, if you like, is the pistons of the heat engine of the hurricane.
The hurricane hunters make it through the eye wall. Inside, a circle of calm weather up to 40 miles across. The eye is the heart of the storm, the pivot the hurricane rotates around. At the center of the eye, the air is relatively still. No rain, blue skies.
When we fly into hurricanes, you don't see much, and you're going through the eye wall. It gets very dark, and then all of a sudden, the plane goes smooth, and we're in the eye, the calm part. And you're blinded for a second because the sunlight is so intense, and your eyes finally get used to what's going on. You look around, and you're in this, it kind of looks like a gigantic bowl. It's like a 40-mile wide football stadium, just what a hurricane looks like.
McFadden's mission is to drop a probe into the heart of the storm.
This is one of our GPS dropsondes, and it's proved to be probably one of the most important tools for collecting data in hurricanes that we've had over the last 10 years.
The probe parachutes down through the eye and measures the hurricane's temperature and humidity twice a second. Built-in GPS gives data on wind speeds and direction. But the most important reading is atmospheric pressure. As the hurricane grows, the pressure at its center drops. The area of low pressure sucks in more warm, moist air. If the hurricane hunters can get a pressure reading from the eye, meteorologists can estimate how powerful the storm may become and how long it may last. They also monitor the size and shape of the eye. As the storm gathers strength, the eye can contract, making the winds even stronger. In 2005, Hurricane Wilma did just that.
What this is a loop of the satellite imagery. And so this gives you a sense of the evolution of the whole life cycle of Hurricane Wilma. And you'll see the development of the eye, very tiny eye. When you get a pinhole eye, a very tiny eye, that's often indicative of a very small inner core. And in general, as the eye and eye wall gets smaller, you tend to have faster winds, stronger winds. It's analogous to an ice skater. As she brings her arms in and she's rotating, she spins faster.
Scientists classify the hurricane's strength according to its highest sustained wind speed, taken over a 1-minute period at 33 feet. Category 1, wind speed 74 to 95 miles per hour. Category 2, wind speed 96 to 110 miles per hour. Structural damage to roofs. Category 3, up to 130 miles per hour. Many buildings irreparable. Category 4, winds up to 155 miles per hour. It smashes solid walls. Category 5, the deadliest. Large-scale destruction and widespread flooding. Little can survive a Category 5 hurricane. In the Atlantic, the approaching hurricane is still a Category 1. Ahead lie 2,000 miles of warm water, fuel for a thirsty storm. The battle now is to predict how powerful it will become and where it will strike. A killer hurricane stalks the Atlantic. 8 days ago, it was just a cluster of thunderclouds off Africa. Now, it's a Category 2, over 200 miles across, winds near 100 miles per hour, and rising. In less than 48 hours, it will hit America. But where?
Nowhere is safe on the Gulf Coast or the East Coast of the United States. And the more we can understand of the dynamics of these storms, the more we can understand what exacerbates the impacts, the better it is for everybody.
It's vital for meteorologists to understand why hurricanes take a particular path. If they can better predict where these killer storms will hit land, they can broadcast more accurate warnings and save lives.
Now, how a hurricane moves is due to a number of different factors, of which there are two main ones. The first is that it acts just like a cork in a stream. It is actually blown along by the large-scale atmospheric winds in which it's embedded. Then the other major component is that they actually use up a little bit of the Earth's rotational effect to allow themselves to push themselves along.
To predict where the hurricane will strike, meteorologists need information about the weather systems that surround it. The trade winds, a prevailing pattern of winds found in the tropics near the Earth's equator, push the hurricane west at speeds of up to 20 miles per hour. But before the storm makes landfall, it must negotiate a region of high pressure off America, known as the Bermuda High. This high-pressure dome moves across the Atlantic and creates winds that spin clockwise. Depending on its size and position, it can steer a hurricane harmlessly into the Atlantic or straight into land.
It's the changes in the wind flow that are important. Whilst however the wind is in one direction, it's great for forecasting because it makes it really easy. It's when they're at that change state that it becomes very, very difficult.
Meteorologists have recorded the paths, frequency, and intensity of Atlantic hurricanes. Where and how a hurricane strikes can appear random. Scientists use computer models to try to establish patterns to better predict where and how powerfully it will hit land. Joe Cione works to improve the data that inputs into these models.
What models are doing are trying to, as closely as they can, simulate exactly what Mother Nature is doing. And once we get to the point where we say, you know, we have done that, we have improved the model's representation of nature, what will result is improved forecasts going forward.
Over the last 20 years, computer models have made huge advances. Faster, more powerful processors, better weather data, and greater knowledge of hurricane anatomy allow meteorologists to make better forecasts. Robert Rogers and his team at the Hurricane Research Division play a key part in piecing together this puzzle.
The track forecasts have improved significantly, but our intensity forecasts have essentially remained constant. They have not improved or improved very little over that time. So we have our work cut out for us, and that's really what we're focusing on now.
Scientists now have a much clearer idea of where a hurricane will strike. Estimating how powerful it will become is tougher. The hurricane tracks 500 miles south of Bermuda. It's now just 36 hours from landfall. It's already a powerful storm. If it hits an ocean current or eddy where the water is even warmer, it could rapidly intensify. The warmer the water, the more powerful the storm.
And it's sort of like you put a bit of turbocharge into your car. Suddenly it's got more fuel, suddenly it can actually start accelerating its intensity, and away it goes.
It's what meteorologists fear most, a storm that gets a kick of energy.
From a forecasting standpoint, that's kind of the nightmare scenario. So whereas, people went to bed one night expecting maybe a Cat 1 to make landfall, they might wake up the next morning and looking at a Category 3 or Category 4.
Scientists don't know why some hurricanes rev up and others don't. The answer may lie in a part of the hurricane called the boundary layer. It's the region at sea level where the hurricane draws its energy, where sea and air interact.
So if we want to really get a good handle on intensity change, we have to understand how the energy is transferred out of the ocean.
Sion is part of a team trying to unravel what happens at the boundary layer. To bring back the data, scientists must skim over waves up to 3 stories high and fly straight into one of the most dangerous places on Earth. The hurricane is 36 hours from hitting America. Winds near its eye blow 115 miles per hour. It's 300 miles wide and still growing. Question is, will it get a jolt of power? Some scientists believe the answer lies in the boundary layer. It's here the storm draws heat from the sea as fuel. Scientists need to refine their understanding of the exchange of energy that happens here and how wind speed, friction, humidity, and air and sea temperature affect how the hurricane intensifies. Until recently, scientists lacked reliable data from the boundary layer. September 2003. As part of an experiment called Sea Blast, hurricane hunter planes flew straight into the deadly boundary zone of Hurricane Isabel.
Sea Blast itself was to look at the dynamics of the boundary layer in a hurricane. We were willing to fly down to 200 feet as long as we can maintain visual contact with the surface.
Below, a churning mass of 40-foot waves. Around them, wind eddies that could swat them out of the sky.
When you're flying that low, you can see every single wave. And some of these 30 or 40-foot waves look visually like they're about to touch the plane.
They flew so low, sea spray drenched the plane.
We noticed that the windshield was turning white while we were flying at 200 feet in a hurricane. We didn't realize, though, that all that salt was coating the engines.
One of the engines had a problem, and we had to secure it, turn it off.
They regained power just in time and limped back to base. Their data gave scientists fresh insight into how wind speed affects the amount of energy entering the storm. As a result, new data was fed into computer models. Data from the boundary layer will improve the accuracy of forecasts. But data from these missions isn't enough. And Operation Sea Blast proved flying through the boundary layer is too risky. How to get more data without risking lives? Don't send people, send a probe.
What you're looking at here is the Mark III aircraft. It's an Aerosonde Corporation aircraft. That we think that this is a very compact aircraft that can do a lot of things and measures what we needed to measure.
Sion's team loaded the Aerosonde with instruments to measure meteorological conditions within storms. It headed toward the hurricane's strongest winds, piloted via satellite.
Only 100 miles since our turn.
In 2005, they flew into Tropical Storm Ophelia.
We rode it up and down, and the aircraft survived that. And this is the first time we've really been able to look at data like this.
The Aerosonde can fly into the deadliest parts of the hurricane and stay there up to 12 hours.
The only thing I can compare it to is what I saw on TV with these Mission to Mars, where the group of scientists send something out and you see them cheering when it finally gets on the surface of Mars. You just feel just a great sense of accomplishment. And for me, it goes beyond that too, because I know what we're doing is really, we're trying to help people. We're trying to save lives.
Scientists hope that in the future, aerosondes will regularly fly into the hurricane's boundary layer and send back constant data. This will improve their understanding of how storms intensify and help them spot the warning signs. The better the forecasts, the more lives saved. 24 hours from landfall, the hurricane has strengthened to Category 5, a 350-mile-wide heat engine. It converts the warmth of the sea into winds over 155 miles per hour. Inside the storm, rising water vapor and churning seas mean the hurricane picks up 2 billion tons of seawater every 24 hours. The rains inside the storm are torrential. The path is set. Hurricane historian Jay Barnes knows what happens next.
Here we have a hurricane about to strike land. We know what is going to happen because we've seen it happen before. A powerful storm, very, very large in diameter, going to affect hundreds of miles of coastline.
A hurricane's biggest killer is water. Not rain, but a wall of water called a storm surge. 90% of all hurricane deaths are from drowning. Oceanographer Stephen Begg watches the Atlantic for the first signs of the surge.
Storm surge is not something that's been seen by very many people, and even fewer survivors, so that it's hard to describe to people.
Forecasters monitor the hurricane closely. From the wind, Ivar Van Heerden picks up clues about the size of the surge.
The stronger the winds, the more water you blow towards the shore, the more surge you're going to see.
As the first part of the eye wall hits the coast, winds accelerate. The surge reaches its peak.
The surge intensifies as the eye gets close because the strongest winds are around the eye. So you then, under the influence of the stronger winds blowing the water landwards, piling it up on top of what's already been piled there, and that's when you get the intensification.
The highest winds blow on the right side of the storm. If the right side strikes first, the surge will be worse. That's because the hurricane is not only spinning counterclockwise, but is being driven by winds across the sea. On one side, spin adds to forward motion. On the other, it subtracts. A storm spinning 90 miles per hour and moving forward at 10 will have winds of 100 on the right side and 80 on the left. The higher the winds, the higher the surge. August 2005. A Category 1 hurricane struck Florida, then transformed into a 400-mile-wide killer in the Gulf of Mexico. It was set to strike the Gulf Coast, right-hand side first. The hurricane's name, Katrina. Professor Van Heerden watches the path that Katrina is taking.
We started to suspect that Katrina potentially could hit New Orleans even before it made landfall in Florida. And the reason being the weather patterns were such. The Bermuda High had moved a little bit to the west, that the wind currents would be bringing anything that entered the Gulf of Mexico into Louisiana. The curvature was there. And of course that proved true.
At 6:10 a.m. on the 29th of August, Hurricane Katrina hit the coasts of Louisiana and Mississippi. In the midst of the carnage is storm photographer Mike Tice.
The storm surge was coming up to Highway 90, and by 8 o'clock, it was already coming to the front steps of the hotel. When the storm surge started to get around 12 to 15 feet, it made it into the first floor of the hotel, and a car comes floating through the hotel lobby. I saw it coming ahead of time in the parking lot. it perfectly came in, so it came directly through the front glass doors, crashed into them, and the horn started honking, the lights started flashing. It was echoing inside this lobby. Of course, all the power's out. It's pitch dark in there. And it is one of the most horrifying, scary things I've ever seen in my life. It was straight out of a scary movie, and I don't think I could ever have imagined I would ever witness something like that in my life.
The highest storm surge ever seen in America sweeps across the entire region.
This rise of sea level in some areas estimated over 27 feet. And if you can imagine the beachfront like we're standing here today, a 27-foot elevation of the surface of the ocean with waves, battering waves on top of that, it's quite destructive. And that's what caused the tremendous destruction we saw along the Mississippi coast.
The surge built along the Mississippi Delta. In New Orleans, the levees burst. A city drowned.
We knew that we were going to be dealing with very high death rate. 10 years of research, looking at lots of other floods all over the world, just cannot prepare you to see miles after miles of subdivision and only the roofs are visible. And of course, on the roofs, people frantically waving for help.
Over 1,500 people died. A tragic testament to the power of storm surge. Now it's the turn of the hurricane's eye to hit land. The storm passes over its own havoc. For 1 hour, the rain stops. Clear skies and sunshine break through. What was destroyed in just hours will take years to rebuild. And still, we have seen only part of the hurricane's deadly arsenal. More damage is coming. The hurricane is only half over. Its other lethal weapon returns for a second attack. Wind. "10 days ago, this storm was a cluster of thunderclouds off Africa. Now it's a hurricane at the height of its destructive powers. The storm surge caused terrible devastation. Winds cause even more. As the eye passes over, the other side of its wall hits, and the winds switch direction. At first, this helps. Floodwaters are pushed back out to sea as quickly as they came.
As soon as the eye goes by, the winds start blowing from the opposite direction and it starts blowing the water offshore, so that you get the very rapid set down.
As the deluge of water drains away, the hurricane begins to move further inland. Its strongest winds, over 155 miles per hour. The eye wall.
The winds are toppling power lines and knocking down trees, blowing the roofs off of homes and smashing windows. It really is a scene of chaos as the most powerful part of the storm strikes the coast. That's when you see the greatest intensity of impact.
Low pressure pulls air in toward the center of the storm as wind. The closer to the eye, the faster the winds. Some of the inrushing air gets pulled into strong updrafts, and centrifugal force generated by the hurricane's spin pushes some air away from the eye. Most rams into the eye wall, creating a spinning tube of wind and cloud. Bob Henson studies the architecture of this force.
So in a mature hurricane, you've got this complex dance, and it's a very symmetric and beautiful thing, actually.
This delicate balance of forces shapes the speed and direction of the hurricane's internal wind.
So what you really have in a hurricane is wind parcels rotating around the center of the hurricane, like the nickel is here, but spinning faster and faster as it nears the center and tries to rise up, and then finally does rise through the very center of the hurricane, as we're seeing right here. That's what actually happens in a hurricane.
A hurricane's strongest winds are just above the ocean and close to the eye wall. Away from the center, winds slowly weaken. Yet even 60 miles from the core, it gusts well over 100 miles per hour. The damage can be colossal. At the University of Florida, scientists are working with engineers to design hurricane-proof homes. The first challenge for Forest Masters is to test buildings under realistic hurricane conditions.
So we're trying to understand how does the whole building perform, in concert to resist these extreme loads.
To test how a building will perform, Masters measures hurricanes at work. His team deploys hurricane-proof towers, loaded with equipment, to measure the winds 33 feet up.
It's incredibly dangerous deploying this kind of instrumentation in the path of a landfalling hurricane. We don't have a lot of time. We wait to the last possible minute to be certain that we know where the storm is going to go.
The data lets Masters map the wind itself. His results confirm the winds change radically once the storm moves off the ocean and hits land. Buildings and even the ground itself cause friction and reduce average wind speed. But as winds are forced over obstacles, gusts become more intense. These turbulent blasts of air can turn a home into matchsticks in minutes. Masters feeds data from the towers into a hurricane simulator. He aims to recreate a Category 3 storm to test how a window performs. This machine really blows. 8 5-foot-tall industrial fans, powered by 4 vast engines, produce the winds. A 5,000-gallon water tank cools this vast machine and provides the rain.
We're taking that turbulence data and we're trying to replicate that at sufficient scale to immerse a low-rise building. And that allows us to look at the performance of all the different parts of the building, such as the windows, doors, and roof cover systems.
The simulator mimics the gusts and driving rain of a typical hurricane. If the hurricane can get inside doors and windows, the difference in pressure can tear the house down. This window is being hit by Category 3 force winds. So far, it's impervious. Piece by piece, the team tests windows, tiles, studying the ways in which hurricanes expose flaws in design and assembly.
Ultimately, if we can make better buildings, stronger buildings, perhaps we can modify our evacuation policies so that people can stay in their homes longer, or, in a higher and more intense events.
As the hurricane travels inland, the value of this type of research is obvious. Buildings with any weakness are ripped to shreds.
My house has just launched a whole bunch of missiles into the air, which is going to damage your house. Your house is going to launch a bunch more missiles into the air, which is going to damage the next house down. And suddenly we have this mass of flying debris that is doing an enormous amount of damage.
The storm moves 15 miles inland every hour. The further it moves away from the ocean, the weaker it gets. Winds drop by half every 7 hours. The hurricane is dying, but it's not dead yet. The hurricane hits land as a full-blown Category 5 storm, a blast of destructive energy. It creates vast floods and devastates coastal towns and cities. But as it leaves the ocean behind, it loses power. The hurricane needs fuel.
When a strong hurricane makes landfall, you see some changes to the characteristics. The structure starts breaking down.
Really, over just a few hours, the death warrant has been written.
The energy source was heat from the warm ocean. Dry land lacks the fuel to keep it going, and the storm's heat engine stalls. the hurricane releases more energy than it gains. Its internal structure, the inflow and outflow of air, disintegrates.
If you're going to write an autopsy of a hurricane that makes land, it probably would say death by lack of warm water, because once the hurricane has moved off the ocean, it's lost that source of heat that sustains it.
Near ground level, the inflowing and outflowing wind meets friction from land, trees, and buildings. The low-level winds die. With no energy coming in, the storm's air circulation falters.
In addition, the winds start to feel the trees and the houses, which impact a lot of friction, and it slowly but surely spins down.
It's like a car running full throttle on an ounce of gas. In one day, a Category 4 hurricane can shrink to a mere breeze. If the hurricane hits mountains, it will die even faster. But sometimes, the storm is thrown a lifeline.
Sometimes a hurricane may briefly re-intensify, and this is a process that's rare and not well understood, but if it passes over very moist land or a marshy area or so forth, it may get a little pulse of energy, and if other conditions are favorable, you might get a brief spin of it.
August 24th, 1992 at 5:30 a.m. Andrew slammed into Florida as a Category 5 storm. After landfall, its winds faded. It limped across Florida for 4 hours, passing over the Everglades. Warm, shallow water temporarily nourished the storm and allowed Andrew to make the deep waters in the Gulf of Mexico. Andrew revived and became a Category 4 storm. It pounded Louisiana. It took another 24 hours for Andrew to die, this time for good. The death of a hurricane marks the beginning of its autopsy by the scientists.
We do an evaluation of the storm itself, the whole life cycle from birth to maturity to decay, and try to summarize that as well as the impacts on people.
Scientists have improved their track prediction by 50% in the last 20 years. Huge advances are being made in forecasting just how strong a storm will become. But they may have to factor in a new twist. What will be the impact of rising global temperatures?
We've had a lot of Category 5s just within the last few years. So there's been a lot of discussion and a lot of questions about are we seeing an impact from global warming on this hurricane or that hurricane?
Climatologists combed through more than a century of records. They found that average ocean temperatures in the tropics have risen by 1 degree Fahrenheit. Hurricanes get their energy from warm water. Logic suggests stronger hurricanes. In 2008, the United States Climate Change Science Program announced their conclusion. It points to an increase in hurricane intensity or strength.
It is very likely that the oceans have warmed up due to climate change. It is very likely that we will see, and indeed are seeing now, increases in rainfall in hurricanes because of this, and increases in the maximum intensity.
For now, meteorologists concentrate on the present. Their work continues to reveal new aspects of the birth, life, and death of the deadliest weather system on planet Earth.
We've reached the point where our meteorologists are doing a super job of telling us where they are, where they're going, and what to expect. Well, one of the things that we can all expect is that they're going to keep coming.
Science has shown us the anatomy of a killer. We can't prevent them, but we can learn to predict them. With each new piece of the puzzle, science saves more lives. The power of a hurricane is awesome. They're striking earlier than ever before.
I realized that this was going to be a historic event.
They're getting stronger.
Is there anybody else in there with you? Do you need help? Is there anybody else down here?
And they're striking places they've never been.
If you're living north of Tornado Alley, sometime in the future, tornadoes will start showing up on your doorstep.
Tornadoes are changing. The events of one tragic day will tell us why. A terrifying glimpse of the future that holds the key to saving lives. February 5th, 2008. Super Tuesday. Out across the Central Plains, a storm is brewing. This will be no ordinary storm. As cold, dry weather streams in from the Rockies, unseasonal warm air forces its way north from the Gulf. Where they meet, history will be made. No one expects to see this kind of weather in winter. The first sign of trouble arrives late in the morning. Massive thunderstorms are forming in a line over Texas.
My initial thoughts were I need to get the word out. It's obvious that we are dealing with a major storm system that will produce widespread dangerous weather and that people are at risk.
And by mid-afternoon, the system is beginning to develop the most powerful storms of all. Supercells. One hour later, the situation on the ground goes critical. The start of a trail of death and destruction that sees 87 killer tornadoes drop from the skies over Mississippi, Alabama, Arkansas, Kentucky, and Tennessee, wreaking more than $500 million of damage. "57 people will perish. One of the worst tornado outbreaks ever recorded. But the implications are far worse. Scientists looking at Super Tuesday see a dark future. Stronger, more destructive tornadoes striking outside the traditional tornado season. Striking in places they have rarely been seen before. Tornadoes are changing. So what exactly is happening? The answers lie in the rubble of Super Tuesday. Solving the mystery of this devastating outbreak is a matter of life and death. The investigators start with the biggest mystery of all. How does a tornado form? From here, they can work backwards and figure out what was different about the storms that gave birth to the tornadoes of Super Tuesday. What they know for sure is that tornadoes form in storms like no others. Hurricanes take days to develop, cover thousands of square miles, and follow a discernible path. They begin life in Tornado Alley. stretching from Texas through Oklahoma, right up to Iowa and Nebraska. Vast and flat, and caught in an atmospheric crossfire between north and south, the weather here has all the right ingredients for twisters, and spring is traditionally tornado season. As winter turns to spring, polar air from the Rockies spills across the plains. It sets off on a collision course with warm, moist air heading north from the Gulf of Mexico. The stage is set. Warm air is light and wants to rise. Cool air is heavy and wants to sink. When the two air masses collide, they begin to spin. Tornado expert Robin Tanamachi has a simple way to demonstrate what happens next.
What we have right now is a very unstable arrangement. You can see we've got this very dense, heavy water up in the upper chamber, and the lower chamber is filled with air, which is much less dense than the water. And the air wants to go up into the upper chamber, the water wants to come down.
Scale this instability up a few thousand times, and you get vast thunderclouds called supercells, the birthplace of tornadoes. Compared to regular thunderstorms, they can span 20 miles across and tower twice the height of Mount Everest. Supercells are the most ferocious of all thunderstorms. But the energy in the storm needs an outlet. The cold air wants to sink, and the warm air wants to rise. In order to restore the balance and release the energy, another ingredient needs to be introduced.
You can see some of the air bubbles are kind of traveling up into the upper chamber, but this is a pretty inefficient way to restore the balance to this unbalanced system. And so what I'm going to do is impart a little bit of vorticity to the system by sloshing it around a bit so that now it spins. And now we have a vortex that's formed in the middle, so that now the air is flowing upwards through the center of that vortex into the upper chamber, and the water is flowing downwards into the lower chamber, so that this is a much more efficient way for the system to go back into balance.
The imbalance allows the warm and cold air to mix by spinning them together. It's the fastest way for the heavy air to sink down. This spinning is known as wind shear. This is the second vital ingredient for tornadoes.
So relatively weak winds at the surface, topped by stronger winds aloft, create this roll, and that is shear.
So they know how supercells are created. But why a supercell creates a twister is the last great weather mystery. It seems clues may lie in the spinning motion itself.
Many researchers who've studied them have sometimes called them accidents of nature because it seems so elusive to figure out what actually went together to cause the tornado at the ground. We know how to get a lot of spin in a thunderstorm, but there are definitely some more complex things going on near the ground. We can have spin taking place on small enough scales that we really aren't able to measure it.
Only one supercell in 4 gives birth to a tornado. So what makes that one so special?
We do not know yet what the mysterious missing ingredient is. We think we know what it takes to get a tornado, but there's something mysterious that we still don't understand that determines, sometimes a tornado will touch the ground, sometimes it won't.
But when it does, the results can be devastating. Once the funnel touches down, it starts feeding on an inflow of warm, moist air at ground level. This warm air is called updraft. Low pressure inside the vortex creates a vacuum, and the warm, high-pressure air around it rushes in. Once inside the funnel, the warm air shoots upward, trying to restore the balance, all the time sucking in more and more warm air from the ground. The warm air is the fuel that gives it the energy to move forward. Its funnel sucks up debris as it tracks along the ground. You not only see it coming, you hear it.
Don't go! Jesus Christ!
There have been descriptions of tornadoes that vary from a roar like a freight train, depending on how fast the tornado is moving. If they're inside of a house, they may report that it makes a very high whistling sound, say if it's coming through cracks in windows or something like that.
Yes, a large destructive tornado. There's a large tornado moving through the south side of Atkins.
On Super Tuesday, one of the worst tornadoes ever seen in Arkansas rips through the state, traveling a record 122 miles. Across 7 counties, it leaves 13 people dead. 100 homes in the little town of Atkins are torn apart. But what makes this tornado so unique is that it happens at the wrong time of year. Powerful tornadoes like this very rarely strike in winter, yet Super Tuesday sees 87 of them. Investigators now turn their attention from the tornadoes to the storms that made them. The answers they are about to uncover will bring them one step closer to understanding why tornadoes are going to get worse. On the 5th of February, 2008, a devastating tornado outbreak claims 57 lives and leaves experts baffled. 87 powerful tornadoes striking in winter is rare.
Once I sat back and realized it was only the 5th of February, then I realized that this was going to be a historic event.
Freak weather? Or is a pattern emerging? To find out, scientists rework the events leading up to Super Tuesday. One day earlier, and meteorologists at the Storm Prediction Center notice a dangerous wind pattern, one that usually occurs in spring. They are surprised to see warm winds moving north, cool winds heading south. When they meet in Tornado Alley, the chances of tornado formation will be high. Yet tornado season is still 2 months off. Why are these 2 spring air masses meeting in winter? The answer is found in a strange ocean current 1,000 miles away in the Pacific. Joe Schaefer, the director of the Storm Prediction Center in Oklahoma, wanted to find out what caused winter tornado outbreaks.
Super Tuesday was in February. To the general public, it probably did come as rather a surprise that you're having this strong activity in February.
He begins by looking for a bigger pattern.
Newest ones are white, the oldest one.
Could the arrival of spring weather in winter be anything to do with La Nina, a vast ocean cooling event in the eastern Pacific? It's a long shot, but he knows it causes extreme weather in the most unlikely places.
There has to be some clues to what Mother Nature is really going to do.
There are always larger patterns at work. The El Niño and La Nina cycle are one of the biggest. The cycle affects vast ocean currents, which govern the warming and cooling of the oceans. The El Niño current drives east, carrying the warm waters of the tropics to the west coast of the Americas. As it does, it warms the atmosphere above it. El Niño lasts about a year. The cycle then reverses and the temperatures drop. This reversal is called La Niña. This current carries cooler seas and cooler air above. The cooler seas of a La Niña year are famous for influencing the increased strength of Atlantic hurricanes. But no one had yet proven a link to tornadoes.
We just looked at the number of tornadoes all across the country and tried to see if there was a relationship between the tornadoes and whether you were in a El Nino, La Nina, which is the opposite, or a neutral pattern, which is neither one. So we looked at those and found absolutely nothing.
Other meteorologists were also searching for a link. But weather systems are some of the most intricate patterns known to science.
People would find one thing, these people would find different conclusions. I more or less had come to the conclusion that there wasn't any link on the thing.
He couldn't believe Super Tuesday was a random event. He was convinced that there was a relationship between events like Super Tuesday and La Niña.
You always have the hope that there's some seed out there of truth, or I never would have looked at it in the first place if I really didn't think someplace in my core that there had to be some kind of relationship.
One day, Joe and his grad student have a brainstorm. Instead of counting each tornado in each year, they look only at outbreaks, days with 6 tornadoes or more. For the years they study, they find twice as many outbreaks occur in a La Niña year than they do in an El Nino year. This doesn't yet explain why the Super Tuesday outbreak occurs in winter. So they refine their search. They begin to focus only on winter tornado outbreaks. They discover that during a La Niña year, winter tornado outbreaks are likely to be more severe. 2008 was a La Niña year. The implications are enormous. Conclusive proof that the winter outbreak on Super Tuesday is caused by the La Niña effect. It's an incredible breakthrough. The mystery of how deadly winter tornado outbreaks can happen is now solved. They realize that La Niña strengthens the cool winds from the northwest, which intensifies wind shear and creates more violent tornadoes. The breakthrough is a milestone in tornado research.
Science is such that if you can actually see the relationship and prove that it exists, then you've made a contribution.
A contribution that may help forecasters save lives in the future. But the mysteries behind the Super Tuesday outbreak are far from solved. We know why it happened in winter, but what scientists now need to find out is why are they so unusually powerful? Forecaster Greg Carbon and his team are the first to spot where the trouble is brewing.
The first watches that were issued across Arkansas were to get the word out that dangerous weather is on the way. Despite the forewarning, despite the watches, and even the tornado warnings that were issued during the event, we still had loss of life.
Nothing can prepare them for the destructive power of the tornadoes they are about to see. Super Tuesday, February 5th, 2008. At 5 p.m., a giant tornado descends on Arkansas. 7 counties lie in its path. The power of this monster is about to take everyone by surprise. Using a system called the Enhanced Fujita Scale, scientists classify the strength of a twister between EF0 and EF5. EF0 can break branches from a tree, and EF2 can lift a roof off. Anything above that is rare. The vortex in an EF5 can reach 300 miles an hour, the fastest known winds on our planet. With wind speeds around 200 miles an hour, the Arkansas tornado is an EF4. And it isn't the only one. Another EF4 tornado touches down in Jackson, Tennessee, 300 miles away. It shreds Union University. Across Tennessee, 1,000 houses destroyed. 32 people killed. Debris is found 70 miles from where it was lifted. Super Tuesday's 5 EF4 twisters reveal an alarming trend. Stronger tornadoes lasting for longer. In a matter of hours, they clocked up more than a quarter of the average annual death toll. To understand why they are so destructive, scientists need to know, where is their energy coming from? Is it also connected to the powerful ocean current during La Nina? If so, how? The first clue lies 30,000 feet above the Great Plains. An invisible force traveling at 300 miles an hour is steering the storms and spinning them faster. A ribbon of wind called the jet stream. It speeds through the highest part of the sky, called the troposphere. The jet stream forms where cool air from the North Pole meets warm air from the equator. As the Earth spins, it sends the air shooting west to east at the point where the two air masses join. As polar air and Gulf air meet, the warm air is sucked up through the thunderstorms and into the troposphere, where it crashes into the jet stream. As the jet stream shoots across the United States and over the tops of the storms, it sucks on these updrafts, spinning up the storm. Just as a gust of wind across a chimney will strengthen a fire, the jet stream strengthens storms. On Super Tuesday, it's winding them up and steering them across the plains.
Here you come, Ryan. I've got the analysis, and it looks like we're starting to see moisture increase across this area and Q coming in. The watches were up. We knew that this potential existed downstream from Arkansas off to the east. It's not that the cells in Arkansas moved directly into parts of Tennessee or across the Mississippi Valley. We now had new development occurring in parts of Mississippi and Tennessee. And that new development quickly acquired supercell characteristics. And the event began to unfold quite rapidly during the evening hours.
By 5:25 that day, the jet stream hurtling across the Midwest was powering up one thundercloud after another. As the monster storms advance on Tornado Alley, some 20 million people are in their sights. When scientists look closer at the events that unfolded on Super Tuesday, they find a compelling piece of evidence that links the strength of the jet stream and the destructive force of the tornadoes to the Pacific Ocean current, La Nina. Because what Dr. Schaefer also discovers is that La Nina not only makes winter tornadoes more likely, it also makes them more powerful. During La Nina, cooler temperatures in the eastern Pacific create stronger easterly winds that make the jet stream flow faster. A faster jet stream spawns stronger tornadoes. They spin faster and track on the ground for longer. The result is more destruction. With such high speeds, the debris a powerful tornado carries can turn into missiles. A stalk of straw can fly fast enough to pierce a telephone pole.
Just hit us. It just blew all the glass out and swooped us up in the air, and next thing I know, we were flipping and flying and landed over here.
Super Tuesday 2008 was one of the worst tornado outbreaks ever. But could tragedy have been prevented? Doug Forsyth at the National Severe Storms Lab in Oklahoma has just set up a new kind of early warning radar station using technology developed by the military. Phased array radar. Traditional radar starts scanning at the bottom of a storm. By the time it gets to the top, the bottom has changed. Too slow to catch every detail of a tornado forming. But phased array radar uses multiple beams that scan in rapid succession.
To improve our lead times, we need to scan faster. With a phased array, if I can do that in less than a minute, then on the second minute, I'm already issuing the warning. So I've already increased my lead time by about four minutes. We're now getting about 13-minute lead time, which is a pretty good lead time, but we'd really like to extend that.
Phased array radar is a 2-for-1 gift. It could be the tool that leads researchers to cracking tornado genesis. And it gives forecasters more time to issue warnings. On Super Tuesday, this could have saved lives. Robin Tanamachi's team now includes a truck with phased array radar. Instead of waiting for storms to hit Doug's radar station, they can go and seek them out.
We in our radar research group feel like we're on the cutting edge using this brand new phased array technology. You get a more detailed picture of the evolution of the storm. You can watch it evolve in much greater detail.
But so far this season, that elusive tornado formation has escaped them. But buried in the data, they have discovered something just as important.
When you get a new data set and you bring it into the computer model and you start studying it, it's kind of like drinking from a fire hose. Your mind just goes off trying to think of all kinds of different things that you can do with this data set and different ways that you can analyze it and visualize it.
After feeding data from a recent storm into the software, Forsyth noticed strange patterns.
We're seeing changes go on in the storm that we've never seen before. There's some waves moving through the storm that I don't think the meteorologists knew existed, because you can't see them when you're taking snapshots between 4 and 6 minutes. You just don't see those things happening.
The brown mass is the storm. The new elements the radar reveals might just be the trigger for the tornadoes, like these waves that seem to ripple through the supercell.
Actually starting to see some new activity in storms that we've never seen before.
If they can detect the waves long enough, before a twister is born, they could gain life-saving minutes.
We're going to have to do some research and see what really is happening. I think we'll put it together over the next few years and make some headway into making better warnings and at least understanding possibly this tornado genesis.
Early warnings will save lives. Buried in the rubble of Super Tuesday lies another life-saving clue. Over 1,000 homes are destroyed on Super Tuesday. Research into new building design shows these losses could be avoided. It has also led to some exciting new insights into what happens within the tornadoes themselves. Investigators combing through the rubble of Super Tuesday discover a frightening truth. Tornadoes are getting more powerful. Is there anything we can do to protect ourselves? The first time wind engineer Partha Sarkar from Iowa State University surveyed the wreckage from a tornado, he was determined to do something about it.
You may survive a tornado, but your entire life is turned upside down because your whole house is gone, whole neighborhood is gone. And that's what bothers me. If you see the cars which have taken a hit from F5, you see it twisted beyond recognition, you know, people are no match for that kind of wind.
On Super Tuesday in Tennessee alone, over 500 homes are destroyed. The cost to rebuild runs into hundreds of millions. Sarkar thinks we can prevent the damage these new, more powerful tornadoes will bring.
We can do something about it. We can design these houses to at least not get completely destroyed. If it's partially destroyed, we can rebuild it. It's completely destroyed and it's gone.
In order to figure out how to protect a building, he has to know exactly what the winds are doing inside a powerful tornado. To do that, he has to make himself one. He contacts tornado expert Bill Gallus.
It was probably a phone call I'll never forget. Partha wanted to design the first wind tunnel that would create a moving tornado and wanted to discuss what ways might we use to create a moving tornado simulator.
This is the result of their collaboration. A twister in a can, 18 feet across and 11 feet high, suspended over a model target. The largest and most realistic tornado simulator ever constructed. It can recreate the same kind of tornadoes that struck on Super Tuesday, from EF1 to the more powerful EF5. It's the only simulator that can accurately measure how the wind loads of a moving tornado affect different kinds of structures.
Once they had the large simulator done and had to throw on the power switch, I think there were a lot of people waiting there and scared to death at what would happen.
In the past, wind tunnel research simulated only straight-line wind. This machine reveals how the circular wind of a tornado can literally pull the roof off a house like a corkscrew. New building design will now incorporate ways to prevent this.
Every time I switch on the tornado, I feel good about it.
But this is not the only insight the machine revealed. In order for the simulator to create a tornado, they add a significant amount of downdraft. Could this be one of the elusive ingredients needed to form a real tornado? The team looked closer. Downdraft is a fast current of air passing down through the center of a rotating storm. We don't yet know how downdraft is created, only that it concentrates the storm's rotation by drawing it inward. Downdraft seems to create enough spin to produce a tornado.
It's possible that tornadoes are created in many different ways, but it seems that this particular idea of getting a downdraft that descends toward the ground almost in the shape of a circle should be something that really does lead to tornadoes.
And if tornadoes are getting more powerful, the simulator could tell us more about how they form and what the winds are capable of. But right now, scientists have a more urgent mystery to solve. It seems something else is happening to tornadoes. They're not only getting more powerful, they're not only striking outside tornado season, they're now striking outside Tornado Alley. Forecasters need to understand why. 7:15 p.m. on Super Tuesday, and Arkansas is reeling from 7 tornadoes. Tennessee is now under attack, and more storms are brewing. The team at the Storm Prediction Center can only watch.
There is a feeling of helplessness, really, at that point, because you see the violent weather unfolding. You know that there's most likely a tornado on the ground. You know that there are communities at risk. But you also know you've done just about everything you can do.
As the monster system rampages across the Upper South, it holds one more deadly surprise. Against the odds, one thundercloud crosses the Tennessee state line, moving outside Tornado Alley into Kentucky. On average, Kentucky sees 10 small tornadoes a year, mostly in the spring. It's about to be struck by 24 powerful twisters in a single night. Winter outbreaks usually occur farther south, in Arkansas and Texas, where tornadoes can feed on warmer air. What's causing them to strike so far north? This phenomenally rare event will lead them to the most chilling discovery yet. Super twisters on course for Chicago. The Super Tuesday tornado outbreak has shown that more powerful tornadoes are now striking outside their usual season. The culprit is La Nina. Its cooling effect at sea speeds up the jet stream winds over land, making winter storms spin even faster. The perfect conditions for tornadoes. But there's one last mystery. Why are tornadoes now striking further north, outside of Tornado Alley? Again, the clues lie in the events of that tragic day. 7:35 p.m. Super Tuesday.
Hey, we can see the contact point on that one. He's close. There's contact on the ground. There's debris.
Kentucky is about to be terrorized by the first of 24 twisters. A state usually considered too far north to see this many. At the Storm Prediction Center, Greg Carbon can do nothing.
When I went home that evening, I had no idea that there were already 14 fatalities. I knew we had deadly tornadoes. I knew that the day before, but the actual numbers and the actual accounts were yet to be known.
As the Super Tuesday tornadoes trespass into new territory, pushing the death toll higher, the storm too is dying. As a tornado feeds on the warm, moist inflow at ground level, the downdraft that created it keeps descending. As the cold downdraft collects at the base of the tornado, it wraps itself around the vortex and begins to cut off its warm air supply. The tornado is slowly strangled by the very force that gave it life. As the last twister retreats, the Super Tuesday storms finally run out of energy. The imbalance that created them is gone, and equilibrium is restored. But what caused the tornadoes to cross state lines? What gave them the power to move so far north, into places they are least expected? At the Carnegie Institution at Stanford in California, climate scientist Ken Caldeira may have stumbled across the answer. Caldeira is studying the jet stream in the hope of harnessing its power.
If we could somehow tap into this energy, it would be really incredible resource for civilization.
Caldeira set out to develop an atlas showing the best places to launch wind turbines into the jet stream. As he charted the position of the jet stream from year to year, he noticed something alarming. Over the last 2 decades, the jet stream has been shifting north. As it moves, it takes severe storms along with it. This would explain why Kentucky got struck on Super Tuesday.
The jet streams act as storm tracks. They guide storms and also affect where storms are created. And so where tornadoes used to be something that was primarily of the southern areas, now we're seeing tornadoes further and further north.
But what pushes the jet stream north? For the answer, Caldeira looks south. For the last 2 decades, temperatures around the equator have steadily risen. The jet stream is the boundary between tropical air and polar air. As the warm air mass around the equator expands, the polar air mass contracts. As a result, the jet stream is pushed further north. What are the odds that global warming caused Kentucky's freak outbreak?
You could think of weather as a chaotic system, a little bit like rolling dice. In the natural climate, we're rolling the dice, and every once in a while it comes up snake eyes, double ones. And you could think of climate change as loading the dice, where you should expect more snake eyes, more storms like this occurring further to the north as global warming continues. If you're living north of Tornado Alley, but you don't get any tornadoes now, you should be worried that sometime in the future, tornadoes will start showing up on your doorstep.
The jet stream is moving north over 1 mile per year. Before long, Chicago could mark the center of Tornado Alley. Scientists calculate that if a big twister tore through the city of Chicago, it could do $40 billion worth of damage and potentially kill 45,000 people. Understanding what caused the tragic events of Super Tuesday 2008 has enabled science to predict that there is worse to come. The groundbreaking discoveries about La Niña and the jet stream will go down in meteorological history.
The key, I think, for us is to not get frustrated, but to learn from these experiences and to take from them a better understanding in trying to help predict significant events in the future.
One of those significant events could be the ultimate nightmare. A super twister slamming Chicago. But by the time it strikes, we may be ready by cracking the mystery of how tornadoes form, buying enough time to warn victims of danger, and designing buildings to withstand the worst. Science could be the silver lining inside the darkest cloud. planet Earth. 4.5 billion years of evolution. It's all going to end. Titanic forces are already at work that will destroy the world as we know it. Scientific investigators take us on an epic journey into the future of the Earth, where apocalypses will wipe out all life and destroy our planet. This is the countdown to the end of the world. Seven and a half billion years from now, Earth will be consumed by fire and vaporized. But by then, it will be unrecognizable, a lifeless alien world. Long before its final moment, our planet could be struck by no less than 7 great catastrophes. One by one, they will turn the jungles into deserts, reshape the continents, and boil away the oceans. Other disasters will destroy the atmosphere, annihilate the animals, and destroy every plant. These are just the catastrophes we can predict. And what of mankind? We could be the first to go. This is the story of the death of the Earth. The first threat to life on Earth comes from the heavens. Right now, a lump of rock and metal, 6 miles wide, traveling at 17 miles per second, could be headed our way. It could strike next week, next month, or next year. But whenever it does, there will be little we can do. We would have very little warning before that threat turns into an asteroid impact. Earth has always been in the firing line.
It could happen tomorrow. It could be 100 million years from now. But it's not a matter of if, it's when.
300 million miles out from the sun, beyond Mars, is the asteroid belt, the rubble of a planet that never formed. 750,000 massive lumps of rock, more than 1/2 mile across. It's an inexhaustible source of planetary ammunition that gets knocked out of the belt and sent spinning across space. NASA astronomer Professor Don Brownlee knows a lot about asteroids. The record of the devastation they bring is hard to miss.
Just look at the moon in the night. You see it's covered with craters, huge craters. Impacts that happen to all the planets that have happened for billions of years throughout our history. So this will happen.
It already has. 65 million years ago, an asteroid 6 miles wide slams into the Earth. The impact throws up millions of tons of rock thousands of feet into the air, fusing sand into glass in a split second. This one impact wipes out the dinosaurs, a species that had endured for 160 million years. So what are the odds of this kind of asteroid strike happening today? Using the visible impact record on the Moon and planets like Mars and Mercury, Brownlee has come up with an answer.
The frequency of impact of a 10-kilometer object from space, a comet or an asteroid, of the kind that wiped out the dinosaurs 65 million years ago, is on the average about 1 every 100 million years.
When it strikes, it instantly vaporizes every living thing for miles around. The sheer force of the impact buckles and cracks the Earth's crust, creating powerful earthquakes. The force of the winds whips up waves, pushing powerful tsunamis onto the land. Within a few days, the dust cloud blocks the sun, plunging the planet into freezing darkness. An endless winter that would last for more than a year. Hidden within the dust is something far worse. A sudden overdose of nitric oxide destroys 85% of the ozone layer. As the dust finally settles, the lack of ozone allows damaging ultraviolet rays to reach the surface, harming billions of people and killing plants and animals with lethal doses of radiation. By the end of that first year, at least 70% of all life would have been destroyed. Those that live underground or hibernate stand a better chance. This is what killed the dinosaurs. And one day, the same thing could happen to us. Not knowing when the next asteroid will strike makes planning difficult and worrying pointless. There is worse to come. Even if we could plan for the next catastrophe, it won't make any difference. Ice sheets several miles deep, pushing down from the poles, will be unstoppable. A global ice age is coming. How do we know? It has happened before, and one of the first clues was pulled from the La Brea tar pits. To find an ice-loving woolly mammoth was a big surprise. To find it in the heat of California was a mystery. Could California have once been covered in ice? Could it happen again? To find out, scientists need a record of changes in the climate, stretching back tens of thousands of years. It turns up in the layers of sediment at the bottom of the ocean. Marine geologist Professor Peter Domenical is searching for clues to Earth's frozen past.
Deep sea sediments are really unique archives of past climate change because the sediments in the ocean accumulate very continuously and very slowly over time. So they present us with this kind of history book of past climate change.
These tiny chunks of rock in the sediment hold the answer to the USA's frozen past and to its future. Deposited 10,000 years ago, how they got here is astonishing.
Icebergs carry all these rocks and they hold them inside the iceberg and then they melt. As the iceberg melts, it drops its load. And that's how we find these big pebbles out in the middle of the ocean.
Icebergs once floated off the coast. As the bergs melted, the rocks they carried from the north sank to the seafloor. 10,000 years ago, much of North America is in the grip of an ice age. But what causes a big freeze? The answer isn't found beneath the geologists' feet, but over their heads, in outer space. The Earth orbits the Sun in an ellipse that gradually changes shape over time. The tilt of the Earth to the Sun also changes. Calculations suggested that the interaction of these changes could flip the climate from warm to cold and back again. It's called the Milankovitch cycle, after the man who discovered it. His orbital calculations showed that the Earth flipped from ice age to warmth 10,000 years ago, the exact age of the sediments Domenical has found.
It was shocking when the evidence came out that there was this very close correspondence between the astronomical calculations and then really the geologic record. People were just blown away.
But what about the future? The orbital effect is called the Milankovitch cycle because it happens over and over again.
We're well on our way, actually, into the next ice age. Something most people don't really fully appreciate. Climate was significantly warmer 5,000 and 10,000 years ago, and then we've been gradually headed into this much cooler climate.
Domenical believes the Earth will be plunged into another global ice age within 30,000 years. If the last one is anything to go by, the next will be worse. Because in the last ice age, there were just 5 million humans. Now, there are 6 billion. Could we all survive? Ice sheets 2 miles thick could cover the land. Cities like London and New York may be buried beneath thousands of feet of ice. Global sea levels could drop 400 feet as water is locked up in ice. Freezing temperatures might last 100,000 years. The food chain collapses. Plants die as they are smothered by ice. Herbivores can no longer find food and die out. As civilization collapses and food and shelter become scarce, our base survival instincts kick in. Dr. Erwin Redlener at Columbia University is an expert in how humans react to catastrophic events. The bad news is, many won't make it.
The major challenges will be to how to keep ourselves from killing each other because of a natural event like a new ice age. Enormous migrations of people trying to escape from the extreme conditions have the potential of causing a tremendous amount of deadly competition for resources, for food, for water, for power.
Billions of people could perish as vast areas of available land are swallowed by ice. But many humans will survive the big freeze in belts of green, north and south of the equator. Here, agriculture will continue, but not enough to support the billions who will now begin a battle to control it.
I think we are hardwired on a genetic DNA level to seek survival at almost any cost. And I think there's pretty good examples of that. People who were prisoners of war, and people lost in hostile environments.
In a few green areas, humans will survive, but the population will be greatly reduced. Civilization as we know it will change forever. And the next ice age is unlikely to be the last. The great ice sheets will continue to advance and retreat, devastating life and civilizations. 250 million years in the future, it gets worse. Life will face an even greater threat and be pushed to the very brink of extinction. The seas will die and the land will become desert. $250 million years in the future, having survived ice ages and perhaps even asteroid strikes, there now comes an even greater threat. The surface of the planet is completely unrecognizable. Life is being pushed to the brink of extinction. This terrifying vision of the future is caused by the same powerful forces that shape the Earth today.
Plate tectonics was one of the two major scientific advances of the 20th century. It allowed us to get an understanding that the Earth is really much more dynamic than we ever suspected.
It reveals that the Earth's surface is made up of a series of massive continental plates that are in constant motion. Where they collide, huge mountains are driven up and massive volcanoes pour out liquid rock. It shapes the face of our planet. Armed with this new information, the geological record opened up like a book, revealing that 250 million years ago, all the continents were united to form a single supercontinent we call Pangaea. This was a hot, brutal world ruled by dinosaurs. Could future movement of the tectonic plates transform the Earth once again into a single vast landmass?
We now know how the plates are moving far more accurately than ever before, and so it became tempting to look into how this might develop if we projected these motions a few million years into the future.
According to Livermore's model, 250 million years in the future, a new supercontinent will form. Africa plows into the Middle East as Antarctica and Australia fuse together. One vast landmass surrounded by a giant ocean.
We end up with a supercontinent which is primarily in the northern hemisphere and a southern hemisphere which is mainly ocean. This will give us a range of habitats within the supercontinent quite different from anything that we see at the present time.
With much of the land hundreds or thousands of miles from the ocean, rainfall becomes non-existent. No plants grow, and as the land absorbs the heat, temperatures soar. It turns to desert.
If we were looking down on the future supercontinent, what we're likely to see is something really rather like the interior of Australia.
250 million years in the future, this new world will be mostly desert, covering over half of the land. So hot and dry that few plants or animals survive. 80% of the species we see today could be wiped out. Those that do survive will have to adapt to less water, less food, and rising heat. Our distant descendants might try to take refuge in the coastal regions. But even here, there's no escaping the dangers of this new world.
Around the edges here, we're probably going to see continuing volcanism, continuing earthquakes.
The tectonic forces that push the supercontinent together are still at work. Now they begin to buckle and split the land at its weakest points. The result is massive earthquakes. Lava exploits these new cracks and bursts out, forming chains of volcanoes. Molten rock spreads over thousands of miles, incinerating every living thing in its path. Life on the land will be tough beyond our imagination, causing mass extinctions. But this is nothing compared with the devastation facing life in the new superocean. In 250 million years, a single supercontinent will dominate the face of planet Earth. It has happened before. By exploring what happened back then, we now know that this single landmass could have a devastating effect on the oceans in the future. A lethal dose of carbon dioxide may cause a mass extinction, which could wipe out 96% of life in the sea. But where will this killer carbon dioxide come from? The biggest natural CO2 producers on the planet are well known, and the supercontinent of the future will have plenty of them. Volcanoes. To understand how the carbon dioxide from volcanoes leads to mass extinction in the oceans, Dr. James Barry has been studying what happens to one particular creature called a brachiopod during similar events.
Oceans became much more acid due to all the CO2 that was released by volcanic ash in over 100,000 years. And that increased acidity of the ocean has caused not only brachiopods, but many other types of animal life to go extinct.
Dr. Barry is trying to understand exactly what happens when carbon dioxide levels suddenly shoot up. Among the first to feel it are shellfish.
These brachiopods are a curiosity. They're one of the earliest sort of real animal life forms that evolved on this planet. 400 million years ago, they were one of the most dominant forms of life on the planet. But they went from 30,000 species down to about 300. They're the poster child for how to go extinct.
Brachiopods had survived everything the Earth could throw at them for hundreds of millions of years. Yet it was volcanic eruptions on land that wiped out 99% of brachiopod species in the sea. Barry's research reveals how. Brachiopods are highly sensitive to carbon dioxide levels. The excess CO2 from volcanoes dissolves in the water, making it acidic.
Once it enters the ocean, it combines and reacts with seawater to form carbonic acid. And that changes the balance of chemistry in the ocean.
As the sea becomes more acidic, the brachiopods die out. In 250 million years, the hard shells of all marine invertebrates dissolve in the acidic water. As their inhabitants die, a big link in the food chain collapses. Their predators starve, and the lack of food goes right to the top of the chain. At the same time as the food chain is collapsing, another brutal consequence of a single supercontinent will be reaching its endgame. 80% of marine species live close to the coastline. With all the land locked up, there's less coast to go around. Competition for the prime real estate gets fierce. The coastline of the future supercontinent could be 70% less than it is today. So the next supercontinent will be deadly. In 250 million years, an arid desert on land and an acid ocean means a mass extinction that will make the death of the dinosaurs look like a sideshow. But amazingly, some plants, some animals will survive. Those that can adapt. Creatures like snakes and spiders that thrive in the heat. Low hardy bushes and types of cacti may be able to evolve. Life will endure for 1 billion years to come. It's only then that the final extinction of life on our planet begins. The end of all life on land. 1 billion years in the future, the world is going to get hotter. All stars, like our sun, go through a cycle of life and death. Today the sun is middle-aged, but in 1 billion years, it will be that much closer to death. As it burns through the remainder of its fuel, internal processes will cause it to expand, bringing its surface ever closer to the Earth. The temperature will soar. It is now 86 degrees and climbing. For mankind, another 18 degrees higher, and we will have reached our physical limit. Blood thickens, strokes and organ failure follows. Sometime in the next 1 billion years, humanity will cease to function. At this point, we will have disappeared forever from the face of the Earth. But other kinds of life will be able to survive. Here at the California Academy of Sciences, Professor Lynn Rothschild searches the history of past extinctions for examples of what creatures might be able to survive in a world twice as hot as today.
What I'm holding here is an ammonite, and these were extremely successful group of invertebrates. They were wonderful predators, and they went extinct at the end of the Cretaceous. Not their fault. They were wonderful at the time, but they went.
As the sun expands and the world heats up, it all comes down to luck. If you happen just by chance to be better suited to the new world, you'll make it. If not, it's just bad luck. And in the brutally hot future Earth, we already have a fair idea who's going to be lucky.
We see animals like scorpions, like we have here, spiders, maybe some snakes that come out at night. And these are so well adapted to living in these hot, dry environments because they prevent water loss. They do everything they can to keep water inside their bodies. They stay nocturnal.
Only the most extreme adaptations can survive. But as conditions become worse, life on land heads toward its final moments. It begins with the plants. Atmospheric scientist Professor James Casting is one of only a few people in the world to have figured out what happens to the plants in 1 billion years from now. He's discovered that a drastic fall in CO2 will wipe most of them out.
CO2 will drop by a factor of 1/2. That will wipe out 95% of the plants on Earth.
Geological processes are at work today that absorb carbon dioxide and dump it in deep ocean sediments. But like all chemical processes, the higher the temperature, the faster it works. Supercharged by the hot Earth 1 billion years from now, it wipes carbon dioxide from the atmosphere.
It will drop down below the level required to sustain plant life. And that's the fundamental food source on Earth. I mean, carbon dioxide is the food of life. It's what makes photosynthesis work. And with CO2 gone, it's a very different world.
Deprived of CO2, plant life suffocates and dies. The last remnants of our green Earth turns brown and dead. One vast desert covers the land.
It's really hard to imagine a future without any plants. I guess the best way to imagine it is to go up into the desert. In a way, it's a very beautiful environment, but it is very barren, and it doesn't seem like home.
Without plants, the food chain collapses. The plant eaters starve, and their predators follow. Animals, insects, reptiles, and mammals. For life on land, everyone's luck has finally run out. There is only now one place on the entire planet that does continue to support life: the oceans.
If you think about why life both originated in the ocean and probably will be forced back into the ocean in the future, it's because the ocean is far more stable than land. If you go out into the desert in the middle of any continent here, the summers are sweltering and the winters are frozen. During that same yearly cycle, the temperature right offshore here nearly stays the same year-round.
But 1 billion years in the future, as the dying sun swells and the temperatures rise, the oceans begin to evaporate. As the water level drops, they become more and more salty. To understand what the oceans of the future will be like, Professor Rothschild has come to these salt ponds outside San Francisco, where seawater is evaporated to produce salt.
What happens here, and you'd imagine would happen on the Earth, is that as the concentration of salt goes up, 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 many of the organisms that we're familiar with, fish and kelp and algae and manta rays and so on, drop out.
It is the end for life in the oceans as we know it. Whales, dolphins, jellyfish, coral reefs, pretty much everything. All gone, unable to survive in the increasing saltiness of the water.
And at some point, you're left with brine flies, a few little worms, and some of the microbes that you see here. And at the very highest salt concentrations, about 10 times the salinity of the ocean, you only end up with organisms called halophile.
It is the halophiles, tiny organisms that thrive in high salt environments, that give the water its red color. This color is no accident.
Now, during the summer, we tend to get tanned. I've been in the pool, I look a little tanner than I would in the winter. Well, these organisms also have to protect themselves from a very strong sun, ultraviolet radiation. And so instead of tanning, they tend to produce a lot of red pigments, carotenoids. These are the same kind of compounds that you see in tomatoes and carrots and so on. And this orangey red pigment helps protect these organisms from the very high sunlight.
With a blazing sun filling the sky and temperatures rising, only these incredible survivors called extremophiles can take it. 1.2 billion years from now, all other life is gone.
As the Earth becomes a very hostile place, we're back to having a world that's only populated by microbes, very much the way it was during the early evolution of life on Earth.
Extremophiles clinging on at the ragged edge of survival in the last remnants of the ocean. The final hammer blow that will end all life is now just around the corner. 1.2 billion years from now, plants and animals have been wiped from the surface of the Earth. Only microbial extremophiles survive in a rapidly evaporating, increasingly salty ocean. For the oceans, time has finally run out. The brightness of the expanding sun boosts average global temperatures to a blistering 100 degrees, nearly double than today. Professor James Casting is investigating the devastating effect this has on the oceans of the future.
Well, we think that the Earth will start to lose its oceans when the sun gets about 10% brighter than it is today.
His findings confirm evidence gathered by Apollo astronauts in 1972. Hydrogen is escaping from the Earth. Water is made up of 1 part oxygen and 2 parts hydrogen. So what the astronauts were seeing was the infinitesimal loss of the oceans into space. Today, this amount is nothing serious, but 1.2 billion years in the future, when the temperature is 100 degrees, the process goes into overdrive. Faster evaporation now saturates the air with water. As this water rises to the top of the atmosphere, ultraviolet light from the sun splits it into its 2 component parts, oxygen and hydrogen. The hydrogen is so light, it floats off into space, lost forever. What Casting discovered was that from full to empty, the whole process of losing our oceans could take less than 200 million years. Without water, life cannot exist. So to find out when this will happen, he had to look at a planet not unlike the Earth that lost its oceans in the same way.
Well, I got interested in the future of Earth's oceans by working on, not on Earth, but on Venus.
Physically, Venus is almost a twin of our planet. And billions of years ago, it might have been even more similar.
May well have had liquid water on its surface at one time, just as the Earth does now. But it was too close to the sun. It lost that water by what we call a runaway greenhouse. It's likely, in my opinion, that Earth will follow the path of Venus at some point in the future.
Studying Venus helped Casting estimate when we will start to lose our oceans. The answer came as a shock.
Well, up until we had worked on this problem, many scientists thought that the Earth would retain its oceans for at least another 3 or 4 billion years. But we were able to show that bad things start to happen much earlier than that. The oceans could be lost in 1.2 billion years.
With the water gone, dry salt crusts like these are all that will remain of the Earth's magnificent oceans. Is this the end for life? Incredibly, a new discovery has shown that even without water, basic life forms can survive. But for how long?
Although we'd known that organisms could live in very high salt, we knew that they could also be trapped in solid salt, but what we didn't know is that while they're in the solid salt, it's more than them being in suspended animation, that they are actually still metabolically active. They're still breathing and eating and excreting and doing all the sorts of things they need to do, but at a very, very, very slow rate. So that was really an astounding discovery for us.
In 1.4 billion years, with the oceans finally gone, extremophiles will survive in the solid salt, but just barely.
These organisms will be able to survive a good deal longer in a salt crust like this, even in the absence of water. They won't be able to survive forever like that, but it'll buy them a little time.
Perhaps another few million years. In that time, their main protection will be the red color that acts as a sunblock. While they live, they will transform the way our planet looks from space.
People always think of the Earth as this beautiful blue planet, you know, the pale blue dot in the sky. But the fact is, for almost half of Earth's future history, it will be a Barbie planet. It will be covered with pink salt.
This is the Earth 1.4 billion years from now. The extremophiles cling on in an increasingly desperate fight, but the rising temperatures as the sun brightens eventually defeat them. By 1.6 billion years into the future, the temperature has climbed to 224 degrees, far above the boiling point of water. Life finally loses the battle. The last remaining extremophile dies.
There are several poignant moments in geologic history. The Earth losing its oceans will be the most poignant of all, because that really will be the end of life as we know it. And unless we've figured out how to colonize other planets, then life will come to an end. It's a pretty sobering thought.
The time of the pink Earth passes. Our planet is reduced to a brown, featureless world. Unless we have found a foothold on another, this is the end of life in our universe. For the next 6 billion years, our dead world orbits the dying sun. Only an astronomer can see this far into the future, to the Earth's final moment of existence. Dr. Robert Smith from the University of Sussex has unraveled the Earth's ultimate fate. But his journey of discovery has taken some unexpected twists and turns. The process begins as the dying sun continues to swell in size.
The sun getting bigger will have severe consequences for the Earth, because we predict that the sun will get at least 200 times its present size.
All stars go through a cycle of life and death. Astronomers know this because they can see stars that represent every stage of life that our sun will go through. In 7 billion years, our sun will be close to death. The sun is now 1,000 times brighter, 200 times its present size, and still growing. The heat literally dissolves the face of the Earth, wiping away the last of its uniqueness.
As the sun gets bigger, the mountains will start to melt, and instead of having high mountains and deep ocean depths, everything will flow into a uniform sphere, be featureless, and very, very hot.
Earth's surface is now melting in 2,500 degree heat. The surface runs with liquid metal. Our planet is utterly unrecognizable, a totally alien world. The end is now close. But Dr. Smith's calculations revealed a last-minute escape might just be possible. $7.5 billion years in the future. The mountains and oceans have been erased from the Earth's surface. The temperature is over 2,500 degrees. It has been lifeless for 6 billion years. Now the Earth itself is about to die. At the heart of the dying sun, helium is reaching a critical stage. It's becoming so dense, its atoms so crowded, that the core is becoming explosively unstable. It now takes on its final form, a red giant, 256 times bigger than it is now. It fills the sky.
First of all, you would see the size of the sun beginning to increase. It would get redder, it would get brighter. At the moment, we're used to seeing it about the size of the full moon. Then it would get bigger and bigger, it would fill more and more of the sky, till eventually when it became a red giant, it would probably fill something like half the sky.
As the sun burns up the last of its fuel, it expands outwards. Now almost 200 million miles in diameter and swallowing everything in its path. Is this the fate of planet Earth? When Dr. Smith first tried to find out, the figures showed that as the sun gets bigger, it loses its gravitational grip on the Earth. The chain is broken, and our planet drifts off into space, potentially escaping a fiery death. It seemed that Smith had saved the planet.
It was a good feeling that we'd saved the Earth, and indeed some of the newspaper headlines said exactly that.
But then one of Smith's colleagues took another look and produced new calculations about the red giant. These seemed to suggest a radically different picture.
When we came to look at the calculations again, we realized that we'd missed something out. We realized that there was a missing effect which we had to take into account, and that's to do with tides.
What they hadn't taken into account are the tidal effects of the Earth on the sun. The Earth's gravity will create a tidal bulge on the surface of the sun, in much the same way as the moon affects the rise of the ocean tides on Earth today. This bulge, in turn, creates a drag on the Earth, pulling it back towards the sun. Smith set to work using the new data to find out just what would happen now.
We didn't know what to expect when we first put in this additional effect. We hoped that even when we put in the tides, the Earth would still escape.
Smith announced a very different set of results. The news was bad. The tidal effect chains the Earth to the sun.
When we came to look at this problem again and put in the extra effects and realized that the Earth would in fact not survive, we decided to call our paper Doomsday.
The surface of the Earth is now nearly 2,500 degrees, hot enough to melt metal. The outer fringes of the sun reach out to engulf the Earth.
We try to imagine what it would look like to see the Earth disappearing. Just be like an asteroid crushing through this Earth's atmosphere. It will burn up completely. It will vaporize, it will disappear, it will become part of the sun, and it will be as if it has never been.
12 billion years of planetary history ends. The death of planet Earth, engulfed in flame, vaporized by the sun, reduced to atoms.
Sort of dust to dust. But it's not such a bad fate, because those atoms, your dog's atoms, your car's atoms, they go out into space, and what do? They end up forming new stars, new planets, and maybe even new people.
It's a cruel act of fate that life-giving stars will one day go bad. Big changes are coming. By understanding how Earth worked in the past and how it works today, science is beginning to understand what the future may bring. The death of the Earth is already laid out in front of us. It's written into its geological past, and literally into the stars above us.